Hey folks, welcome back to another lecture in the Introduction to Earth Sciences lecture series. I'm Dr. Matthew Wielicki. Please follow me at Matthew Wielicki on Twitter and subscribe to this YouTube channel if you have the chance so you can get notifications when there's a new lecture put up. I have recently updated my Substack as well. It's called irrationalfear.substack.com now. If you have a chance to subscribe to that, even if you can just check it out, there's a free subscription. Well, you'll get quite a few of the posts that I put up. Every once in a while, there'll be some podcasts or a few posts that are behind paywalls. If you have the means, please subscribe to that. As you know, I am now officially a professor in exile, so that would help me dramatically. Today, we're going to be talking about volcanic eruptions. We're shifting gears a little bit, moving out of discussions of our different types of minerals and rocks. Last lecture, we talked about earthquakes, so we're going to kind of continue on with some of the natural hazards. And we'll talk about volcanic eruptions in this lecture, and then in the next lecture, we'll talk about mountain building. And then we'll start to shift gears a little bit too and talk about Earth's history and how we figure out relative time and absolute time in our rocks and sediments. And then eventually we'll move into the hydrologic cycle, and we'll finish with a couple lectures on climate, but I'll have a whole lecture series devoted to climate coming up soon as well. So this is an image of probably one of the better documented explosive eruptions that we've had. This is Mount St. Helens, and just by chance there was an amateur photographer who was taking pictures of the mountain a few tens of kilometers away, and this was a time period. So this is 1980. This is it's not an automatic drive. You're actually advancing the film with your hand, and so he is taking shots every 10 to 20 seconds or so as he's advancing the film and snapping another photo. And just by luck, he happened to catch the eruption that occurred at Mount St. Helens in 1980. This was a massive explosive eruption. Thankfully, this wasn't surrounded by a large city or any sort of population density. So although there was still some loss of life, tragically, the loss of life was nowhere near what it would be in terms of some of these other larger volcanoes that are near urban centers that we'll talk about here in a few minutes. And we'll come back to this and talk about why this was an explosive eruption and why it had this style of really a huge explosion as compared to something, for example, like Hawaii, that has essentially been erupting continuously since the 80s. And I'll show you some pictures of me sampling some lava there in Hawaii. And I wasn't ever in fear that the mountain was going to explode like Mount St. Helens, and actually comes back to the rock types and the magma, the chemistry of the magma below the surface. That's why we kind of talked about different chemistries of rocks prior to moving into this lecture about volcanic eruptions. Volcanoes are kind of unique in the fact that they are one of these natural hazards that could have global effects. An earthquake can have pretty large regional effects, and if the earthquake occurs in the oceans and there's a tsunami, those effects can hit coastlines that are thousands of kilometers away, but essentially it's going to be isolated to a certain region. Volcanoes are kind of unique because in large volcanic eruptions, there could be enough material that is thrown into the atmosphere that there's actually global effects. And there's a good historical record of this in 1816, which is known as the year without a summer. And this is an image in the upper right of New York, and this is in June, early June. And so this was a time period where it should be nice and warm and humid, and there was snow on the ground, a few inches of snow on the ground. And you may think, well, what's the big deal? Well, June is the time when you're really starting to get your crops going. You're out of any possible freezes, and your crops are now, starting to grow, and 6 inches of snow onto crops that are maybe 6 inches to a foot tall can be very detrimental. And in fact, what we saw was huge crop failures in terms of things like rye and bread. So that's the lower image. You can see how the price of those materials almost tripled, went up 2.5 times in certain places. That drove up, obviously, food prices of things like meats. And this was really unknown why this had happened. In 1816, the world wasn't as interconnected, obviously, as it is today. But it soon became evident to scientists that this was related to an eruption on the other side of the planet. This was an eruption in 1815 for the Indonesian volcano known as Mount Tambora. And about over a kilometer, or close to a kilometer and a half of material was removed from the upper portion of the mountain. Excuse me. You can see that large crater that is now present in the center of the mountain. Well, when we look at Mount St. Helens, in fact, you'll see that Mount St. Helens looks very similar. Much of the upper portions of the mountain was actually removed during the eruption. And a lot of that material is broken up into chunks and pieces and gets thrown up into the atmosphere. And it was this ash and this dust that actually led to this lowering of global air temperatures. Tragically, the estimates are something like 70,000 fatalities from this eruption. Indonesia tends to be a pretty highly populated area with high population densities surrounding many of these volcanoes. And I don't think there's really any estimates for the global impact of this type of temperature decrease. The material that went into the atmosphere doesn't really stay around too long. We're talking on the order of a year or two. We saw temperatures recover pretty quickly because these are particulates that get up into the stratosphere and things like that. And that particulate matter starts to condense, and because it's a solid, it's not a gaseous phase. It's affected by gravity more, and so these things rain back out onto the surface of the Earth relatively quickly. But we've never actually experienced an eruption of a supervolcano, but we're still on the order of probably a few years, maybe a decade at most. There's quite a few hazards associated with volcanoes. So obviously what we just talked about, the ash cloud and the resulting short-term cooling is one. The ash blocks solar radiation from reaching the surface of the Earth, and that solar radiation is really what heats the atmosphere. And so if you block that solar radiation, you start to rapidly decrease global temperatures. But also there are greenhouse gases that are erupted, and so things like water vapor, which is by far the primary greenhouse gas in terms of its effect, and CO2, those types of effects will lead to more long-term warming. Those are gases, so they don't rain out of the atmosphere nearly as quickly as the particulates like the ash and the dust. And so those have a much longer term warming effect. There's also gases like sulfur dioxide, hydrochloric acid, hydrofluoric acid. These things can produce acid rain, kill crops, kill livestock. Actually, in the lower picture on the left there, that's some dead cattle that was in an area near a lake in Cameroon. This lake traps a lot of CO2 in the lower portions of the lake because it's actually a crater lake that's near a volcano. And every once in a while, this lake will turn over, and essentially there's a current that moves deep water up to shallow surfaces and shallow water to deeper areas. And when that deep water that has quite a bit of CO2 dissolved into it reaches the shallower portions of the lake, it outgasses, just like popping the top off of a soda bottle. And that CO2 will actually leak out onto the surface of the Earth, and it will settle in low-lying areas because the CO2 is heavier than the O2 or the N2. That's the predominant two gases in our atmosphere. And as it settles into these low-lying areas, it actually displaces the oxygen as well as the nitrogen. And thus these livestock actually suffocated due to a cloud of CO2 actually filling in this little valley or this little drinking hole where you can see the mud. And so this is one of these tragic hazards that can occur with volcanoes that we don't really think about as much. Some more recent types of hazards is that they can shut down flights. So this was a large eruption in Iceland in 2011. I started my PhD at UCLA in 2008, and this was my first time I was invited to go speak at a conference at the EGU, the European Geophysical Union, and I was very excited to go. I had, if you're an invited speaker, even as a graduate student, there's usually funds available for you to go, so they had paid my trip to go. And a day before we were scheduled to leave, this eruption occurred, and this eruption was spewing so much ash and dust into the atmosphere, and it was directly in the flight path of flights from the US to Europe, that they canceled flights for 3 days. Over 900 flights were canceled, and my flight was one of them. And I was arriving 2 days before my talk, and I ended up actually not being able to give that talk. I didn't even go, because at that point I would have arrived with only 1.5 days left in the conference. And so this was one that was pretty near and dear to me, that affected me pretty directly. You can see some volcanic lightning occurring there. This is something that people have been studying quite often, or quite recently, as a relatively new phenomenon that's identified. This has to do with static electricity and static charge being built up as these little particles are interacting and rubbing against each other. You can have a lot of this volcanically induced lightning. But thankfully they canceled these flights, because there was a flight in 1982 that flew over an ash cloud by mistake near Indonesia, and all 4 engines failed. So this particulate matter, even though it's very fine and it's a very fine dust, if it gets into the turbines of jet engines, it can do a lot of damage. Thankfully, this flight was able to restart enough engines to fly to safety. I think they got 2 of the 4 engines back up online, 1 on each side, and they were able to land safely without any sort of tragic events occurring. But it was pretty clear to the airline industry that if there was any sort of eruption and there was any chance that this material was in the flight path of airliners, that they were going to either cancel flights or divert flights. It's tough to divert the flights over the Atlantic because you're already on a long haul journey. And so in terms of fuel recommendations and carrying enough fuel that in case something happens, you could circle an airport or something like that. And so they just decided they elected to cancel those flights in 2011. And unfortunately, I didn't get to go. But I would have much rather been at home at UCLA than worried about engines flaming out at 30,000 feet flying over to Europe. One of the earliest recorded eruptions was actually in Mount Vesuvius. A lot of the terminology for volcanic activity actually comes from Italy, and you may have heard of the town of Pompeii. This was an area that was buried by a flow that came down the mountain, which is Mount Vesuvius in Italy. This is an active volcanic region. There's a subduction zone. There's a portion of the plate that is being subducted underneath Italy. And as it gets subducted, it heats up. That magma rises due to a buoyancy force and eventually reaches the surface. And it was an eruption in the 1st century on Vesuvius that was really one of the first well-recorded eruptions that occurred. And then subsequently, many centuries later, Pompeii was discovered and is now being excavated. And we'll look at some pictures of that. So here's an image of Pompeii. So this was the Vesuvius eruption in 79 AD. In the image on the left, you can see an artist rendition of what we think the volcano would have looked like prior to the eruption. So you can see how much of the mountain was actually removed in this large explosive volcanic eruption. And unfortunately, there was a city nearby, the city of Pompeii, and one of the flows, which we define as pyroclastic flows, we'll define that here in a few slides, but this is essentially very hot ash that's coming down the mountain due to the effects of gravity. It rolled over the city. This material is flowing, and it's on the order of hundreds of degrees Celsius, and it's moving very rapidly, and it overtook the city. And unfortunately, it is so hot that it basically cools when it hits your skin, but it burns people's skin and essentially kills them relatively instantly. And it preserves their bodies because that ash cools around their skin. The majority of your body is moisture, right? And so as that water and blood and things like that interact with the ash, it cools the ash very quickly. And it's remarkable some of the images that you can see of people trying to protect their children or huddling down low behind structures. And unfortunately, there was so much ash that the city was buried up to about 13 to 20 feet of volcanic ash and wasn't actually discovered till centuries later. And if you go to the Naples area today, you can actually tour some of these. It's very heartbreaking to see some of these images. But I think it's a motivating factor to understand how volcanic eruptions work, because there's quite a few people that live in the surrounding areas of Mount Vesuvius today. In fact, this is an image of Naples. This is looking down towards Pompeii. Pompeii would be on the other side of Mount Vesuvius. That's Mount Vesuvius there in the background and Pompeii in the foreground. There's approximately 3 million people in the surrounding areas right now. And we know that the plates are continually being subducted, so there's magma being formed beneath the surface. And thus, it's not a matter of if, but rather a matter of when this volcano will erupt again. This is very analogous to what we talked about with earthquakes. And part of our understanding of how these processes work is to be able to provide sufficient warnings such that we can mitigate loss of life. And obviously, we're not going to move these tall buildings and these beautiful churches, but if we can provide enough warning to get people away from the volcano itself prior to an imminent eruption, we hopefully can mitigate some of the loss of life that is associated with these events. Here is one that's more local to us in the U.S., if you're listening here in the U.S. So this is Mount Rainier. That's downtown Seattle there on the left. You can see the Space Needle on the right-hand side of that image, and that is Mount Rainier in the background. And we know that there are flows that have reached to where modern-day Tacoma and Seattle are. And again, this mountain is overdue for an eruption. You can see it doesn't have that same crater, for example, that Mount Vesuvius had, or for example, I'll show you Mount St. Helens has today. And so we know it hasn't undergone an eruption in quite a while. And there is a subducting plate off the shore of the northwest U.S. That's what's creating the Cascade Volcanic Range that Mount Rainier is a part of, and that's what Mount St. Helens was a part of when it erupted in 1980. And so this is a large population center on the order of about 20 to 30 miles away from an active volcano that will erupt again one day. So that's kind of what motivates, I think, earth scientists to study these types of phenomenon and try to understand them such that we can mitigate some loss of life in the future. The original term volcano comes from Volcano, Italy. And Vulcan is the god of fire, and so this made sense. This was one of the first places that volcanic eruptions were identified and were recorded well in terms of scientific records being kept. And so this is where the term originally comes from. And when we talk about volcanic eruptions, we have a really simple definition. We're talking about the transfer of material from inside the earth to the planet's surface. And so we're talking about magma that's in the earth. Remember, our definitions of magma and lava are that magma is concentrated within the earth, so it's an intrusive body. It's intruded in the crust somewhere. And lava is the extrusive form of magma. So lava is when this molten material reaches the surface. So essentially turning magma into lava is the definition of a volcanic eruption. And these are two images here that you can see. One is on the left, that's Mount St. Helens. That's about 42 seconds after the initial landslide that started the eruption. And then on the right is one of the fissures that exists on the big island of Hawaii. And you can see the big difference in terms of the way that they're erupting. The products of volcanic eruptions are essentially lava flows. And that should make sense, right? And so remember that lavas are the molten material that's flowing on the ground, on the surface of the earth. It's going to solidify very quickly because the coolest portion of the earth is at the surface. Pressure and temperature go up as you go down into the earth. And so material that gets to the surface of the Earth is going to cool very rapidly. And that material is going to be at the mercy of viscosity. So it's going to behave dependent on how viscous it is. And remember, viscosity is the resistance to flow. So melts with a high viscosity, they don't flow very easily. I like to think of, for example, honey. Take honey out of the fridge, and it doesn't really want to come out of the bottle. It's very resistant to flow. It's not a solid by any means, but it's very, very thick. It's very viscous. Right? And you put it into, for example, the microwave for a few seconds, and you can warm it up, and then it will start to flow out of the bottle. So some of the factors that affect viscosity are temperature, volatile content, so that's going to be things like water and gases that are dissolved into the lava, and then the silica content. So a rule of thumb is that a hot lava with a high concentration of volatiles and a low concentration of silica will flow very easily. And that, remember from when we talked about igneous rocks, we talked about what minerals will crystallize first or what minerals will melt first. And it's the mafic material that melts last but crystallizes first, meaning it has the highest melting temperature. And so it's the mafic material that can be the hottest. And by definition, mafic means low in silica, and they're usually high in the concentration of volatiles. So it's really mafic lavas that can flow very easily, and felsic lavas that have a really high viscosity and they have a high resistance to flow. When we name lava flows, we just name them by their chemistry. Again, this comes back to the viscosity, because the viscosity is really dictating how the material behaves, and the viscosity is dictated by the chemistry. We name these by essentially the rock type that they will form. So remember, a mafic lava at the surface, the rock type that it forms, we call basalt. So we call those types of flows basaltic flows. If you have an intermediate chemistry between felsic and mafic, we call that andesitic flows, because the rock type that is formed is known as andesite. And then if you have felsic chemistry, which means high in silica content, low in temperature, low in volatile content, you have a rhyolitic flow, and that's because, again, the type of rock that would form from this would be known as a rhyolite. So let's look at some of the characteristics of basaltic lava flows. So here's our image again of Hawaii. This is one of the volcanic vents on Hawaii. Hawaii's kind of unique because it's a hot spot. The top of the volcano itself isn't always the source of the lava. Hawaii has quite a few fissures and vents that are active along the flanks of the volcano. This might be because the hotspot is very large, but also partly because the Big Island is moving off of the hotspot, so the main volcano is actually being pulled away. And that's how we know how the Pacific Plate has been moving over time. We talked about this a little bit in the plate tectonics lecture. But this is a basaltic lava flow. You can see it's very dark in color. It's creating that dark rock that we kind of associate with lava flows. When we think of Hawaii, we think of, for example, black sand beaches. That's because it's very low in silica. It's very low in viscosity. You can see this lava flowing pretty rapidly. They can flow for essentially like water for tens of kilometers, if not hundreds of kilometers. In fact, one amazing thing, if you ever get a chance to go to the Big Island of Hawaii, is to see lava pouring into the Pacific Ocean. You're far from the vent. You don't really have to worry about anything near the vent. And it's because of the lava being such a low viscosity that it can make its way across the island for these long distances. Sometimes it's contained in lava tubes, and that keeps it warm for longer periods of time. But eventually it can pour into the oceans. And it's a real spectacular event to watch this very hot material interact with the water. It turns the water into steam instantly. It quenches the lava very quickly, and it creates this very beautiful scene of hot molten rock pouring into the relatively cool Pacific Ocean. These are some of the lava tubes that I just mentioned. So this is one of the ways that this lava can travel very long distances. So the image there now is Mount Etna. This is in Sicily in Italy again. You can again see the black color. Notice that there's some dark material on the surface of the lava. That's the material that's cooling very quickly because it's interacting with the atmosphere. And occasionally it can cool so quickly that it can create a roof. and that roof will essentially be the upper portions of a pipe or a tube, which we call a lava tube. And so this is the empty space now where this scientist is standing on the right, where you can actually travel through these as the lava exits and the fissure or the vent stops producing new lava. That material drains away and it actually leaves a cavity. And this is some of amazing places that you can go visit, for example, in Arizona around the San Francisco peaks. There's some amazing lava tubes that you can go into. In fact, it was some of the first refrigerators that existed, because prior to refrigeration, if you can get pretty deep underground, the temperature didn't vary very much. And so obviously in the summertime and in Arizona, it can get very hot. But if you could get somewhere underground, and this is long before refrigeration or long before we had large excavating machines that would be able to dig out these areas, they found these natural lava tubes. There's quite a big volcanic field around the San Francisco peaks, around Flagstaff. And they identified that these areas would stay relatively cool as compared to the surface that was reaching in above 100 degrees Fahrenheit. These areas would stay in their 60s or something like that. And so this became some of the original refrigeration that people found. There's a few Hawaiian terms that are used to denote what type of basaltic lava you have. So Hawaii, because it's been erupting essentially since 1980, it's become the #1 place for research on active volcanoes, and so many of the terms come from Hawaiian. So this is this kind of ropey lava or basaltic rock. It has this almost braided look to it. This is known as pahoho. And this is very different than this type of blocky lava, this very kind of rubbly surface that's known as a'a. This is actually an image from Sunset Crater in Arizona. This is very close to the San Francisco peaks where we were just talking about. But almost everywhere where you have basaltic lava reaching the surface, it either has this kind of ropey, braided-like texture that's relatively smooth, or this much blockier, rough texture that is known as a'a. The first one's known as pahoho. I like to remember it as, if you imagine walking barefoot on this type of material, you'd be going, ah, ah, ah. So here's an image of these two kind of coinciding. So it all depends on the amount of volatile content and the amount of heat in the system. But you can see here that this is a a'a flow that's covering a previous pahoho flow. You can see the pahoho has that very smooth texture. You can imagine walking on that barefoot, obviously if it wasn't very hot, and you wouldn't really hurt yourself. And then this a'a that's very blocky on top, very jagged. In fact, when we hike on these flows in the Big Island of Hawaii, we wear gloves, because if you just slip and fall and you put your hand down on some of this a'a, it will cut you instantly. It's so jagged, it's essentially glass. And it destroys your shoes, first of all, so you kind of take some junker shoes that you're going to throw away, plus they might melt. And you have to wear pretty good gloves, because anytime you step or misstep and you have to put your hand down, you would be a bloody mess if you didn't have good gloves on. One other type of basaltic flow that is kind of unique to a certain situation is known as pillow basalts. So remember that at a divergent plate boundary where new oceanic crust is being formed, it's basaltic rock that's coming up. This is mafic lava. It's decompression melting as the lithosphere is thinning, and that's what's creating the spreading centers that Harry Hess eventually identified and proved Alfred Wegener right, and came up with the theory of plate tectonics. At the bottom of the ocean, the water's very cold, on the order of 1 to 2 degrees Celsius. And so when the lavas are coming to the surface, they're quenching instantly. And so you're never actually getting a flow. You're getting these cracks, and a little bit of lava comes out and then it instantly freezes, but then there's pressure because there's more lava pushing in. And so then it cracks again, and you get these kind of round bulbous features that we call pillow basalts, because they almost look like these little round pillows that are sitting at the bottom of the ocean. Occasionally these get exposed on the surface of the earth, but this is a telltale sign of a divergent plate boundary at some point in the past. Rhyolitic flows are very different. So this is an image of Panem Crater. This is on the eastern portion of California, where we have the Long Valley caldera. There's been active volcanism in that area for hundreds of thousands of years. And this is associated with felsic lavas. And so this is material that's coming out that has a very high viscosity. So it doesn't want to travel at all. It's not going to go more than 1 or 2 kilometers. In fact, most of the time, what happens is it kind of stays within the crater and creates a dome or so, or a blocky material within the crater. So here is our naming scheme that we used for igneous rocks, and you can see that we're essentially just using the name of the extrusive member of both the felsic, intermediate, and mafic rock type to denote what the lava type was. So that's where the names rhyolitic, andesitic, and basaltic come from, is that those are essentially the rocks that are going to be created from those types of flows. We don't worry about the intrusive end member because we're talking about volcanic eruptions, so by definition we're only going to be talking about lava since this is at the surface of the earth, so we ignore the name components for magmas. And so here's a graphical representation of what those flow patterns versus lava compositions would look like. So in the upper portion, we have what's analogous to what we're looking at in terms of Hawaii, where we have a vent somewhere near the top of the mountain or maybe on the flanks, and we see that the lava flows are traveling over long distances because they have a low viscosity. And then in the bottom, we have what's analogous to Panum Crater that we looked at on the eastern portion of California, where the material that's coming out is so viscous that it essentially just creates a dome within the crater. So what's all this have to do with a farmer in Mexico by the name of Mr. Pulido? Well, before the mid-20th century or so, it was assumed that volcanoes just existed forever. They were portions of the planet that were, for some reason, very hot. And where we had volcanoes, that's where they were since the dawn of time, and that's where they would remain. Remember, this is prior to the plate tectonics becoming a very well-established theory. In fact, this is just when some of the new data that Harry Hess is putting together to eventually write his seminal paper in the early 60s about seafloor spreading. And so it was on this farm in Mexico, in Mr. Pulido's farm, that scientists started to understand that volcanoes have a life cycle. And in fact, what happened was that this beautiful farmland started to look like this over a relatively short period of time. There was multiple cinder cones that evolved along the farm. You can see all the ash now in the surrounding areas. Obviously, the land is no longer viable for crops at the moment, although volcanic ash is a great fertilizer. When there's enough of it like this, it's going to kill any of the crops. But this made people start to realize that volcanoes come and go. They have a life cycle. They're not infinite. They're not here forever. And so this really started to make people think about the inherent risks of volcanoes. When are they active? When are they not active? Where will new volcanoes start to occur? And so scientists really started to piece together how volcanoes evolve in the mid-20th century. So this is a very young field. What are some of the debris that comes out from a volcano? We talked already about lava flows. That kind of tends to be the most common type of material that comes out of a volcanic flow. But not always is the material coming out such that it's flowing on the surface. In certain types of eruptions, the material is coming out with so much velocity that it's actually being thrown through the air. We call this pyroclastic debris. So pyro meaning fire or hot, clastic meaning a fragment of a rock, and then debris. So this is fragmented material that's coming out of a volcanic eruption and it's landing on the ground or possibly the seafloor in a solid form. And you can see in the image on the left how the drag of the air as it's flying through the air is actually shaping the material into this somewhat like a football shape. A football is shaped that way such that you can throw it over long distances. The nose is pointed such that it cuts through the air, and then the air wraps around to the back, and just the natural drag of something coming out that's soft will take this shape as it's flying through the air, but as it's flying through the air, it's also cooling, and so it lands on the ground with these distinct shapes. We usually classify this material by its size. And so we have pyroclastic debris from basaltic eruptions. These are relatively weak eruptions. We'll talk about this again a little bit more, but it comes back to the viscosity of the magma below the surface. And we essentially denote this material by size. So if it's very tiny, we call it ash. If it's on the order of a centimeter or so, we call it lapilli. Again, this is a Latin term for little stones. And then if it's larger, on the order of 5 to 10 centimeters, maybe the size of an apple or something like that, we call that a bomb. And so it just depends on how big the material is and how it's been flying through the air. Depends on what the name that we give it. When we talk about lapilli, there's essentially two kinds. There are pumice lapilli. This is material that is very frothy. So we talked a little bit about pumice when we talked about igneous rocks. This is one of the only rocks that can float. You may use this in the shower or in the bathtub as an exfoliant. This is because it's full of bubbles. We also have accretionary lapilli. So this is material that is more analogous to, for example, hail. If you've ever seen a hailstone that's been broken when it hit the ground, and you look at the inside, you'll see that it has these concentric rings, because hail, many times it starts to fall, and then it catches some moisture around the outside, but then it gets caught in an updraft, and then when it gets caught in that updraft, it moves higher in the atmosphere, thus it cools. That layer of condensated water around it freezes. It goes through this cycle multiple times, and it has these concentric rings that grow around it. This is very analogous to accretionary lapilli. So sometimes as an eruption is going on, this material is getting thrown up into the air. It starts to fall, but there's another pulse, or it gets caught back into the volcanic cloud that's moving up because of the buoyancy force and the force that it's being erupted at. And so it can go through this process multiple times and actually accrete these layers. It's really the volcanic ash, though, that reaches the highest altitudes and has some of the largest global effects. This was what led to the year without a summer that we talked about earlier. This is also what tends to have the largest regional effects when we talk about eruptions affecting the regions or local regions around the volcano. So this is an image, again, of Mount St. Helens eruption. This was a very explosive eruption that we'll talk about more, but you can see the ash raining back out. So the ash will reach very high altitudes, but it'll start to rain back out. And the ash itself usually isn't too damaging. If you're far enough away that you just get a few centimeters of ash, it's not, it wouldn't be too major of an event. But if there's enough ash that falls on, for example, buildings and rooftops, so this is an example of a restaurant that was in the vicinity of Mount St. Helens, and if there's any rain that's associated with that, or rain that comes in after, that ash will actually become so heavy that it can cause the collapse of roofs and buildings. And so you can see these people on the rooftop there trying to sweep all that ash off. You can see the piles of ash in front of the two vehicles that are in the parking lot there. They're getting rid of that ash because if there's any sort of moisture that comes in the form of precipitation, anytime that ash is on the roof, that added weight can actually cause the roof to collapse. This is the remnants or the ash distribution of the 1980 Mount St. Helens eruption. And so you can see it's on the order of about a trace to a half an inch, all the way into places like Colorado and Nebraska and the Dakotas, even in the edge of Minnesota. There's this one little area of ash that accumulated in Oklahoma that's likely due to a high pressure system that was in that area. When you have high pressure, you usually have falling air, and so that's material that was caught up into the atmosphere but then came down in that high pressure system. But again, you're talking about an order of a trace to a half inch in this regional area. If you look closer to eastern Washington and central Washington, where Mount St. Helens actually is and erupted, you can see that now we're getting into on the order of 2 to 5 inches in certain areas, and that becomes enough that you're going to have major effects to things like crops, and you have to worry about building structure, especially since these are areas that can get quite a bit of precipitation. Now, Mount St. Helens was a relatively small eruption. And when we're thinking about the amount of material erupted, we like to think about it in cubic miles or cubic kilometers. When we think about Mount St. Helens, we're talking about on the order of 0.1 or so cubic miles of material. And that was a relatively small eruption. The Mount Tambora eruption that created the year without a summer in 1816, we think was on the order of about 120 times that size, so 12 cubic kilometers of material. It was much more difficult to estimate because obviously in 1816 we don't have nearly the same type of monitoring we did in 1980, but that's the best estimates that scientists can come up with. Now we compare that to some of the supervolcanoes that exist in the United States. So we talked a little bit about the eastern portion of California, where we have the Long Valley caldera. So that released on the order of 10 times what Mount Tambora released. And then we have two major eruptions in Yellowstone. And so Yellowstone is also an area that's a supervolcano. It's a hot spot. We think that the amount of magma that's below the surface is significantly greater than what is on the surface or underneath the surface, for example, of Mount St. Helens. And these eruptions, we're talking on the order of 2,000 to 5,000 times the material that was coming out during the eruption of Mount St. Helens. So you have to think about areas that during Mount St. Helens had a trace of ash or maybe a half inch of ash. Well, if you start to think about that, these supervolcanoes are producing 1,000 to 5,000 times more material. You're talking about a significant amount of material that would be raining down over a much larger area than, for example, what happened in Mount St. Helens. Just because there's so much more material, the jet stream can carry it longer distances before it all rains out. When volcanic ash gets erupted and thrown into the atmosphere, gravity starts to act on it relatively quickly. So it's being forced out under pressure, so it has this force that's pushing it up into the atmosphere. It's also very hot, so there's a buoyancy force there, but it cools relatively quickly and it gets away from the cloud very quickly, and so gravity starts to take over. And as that gravity takes over, what happens is some of the ash starts to return to the ground and flow down the flanks of the volcano. And this has been known as what we call a pyroclastic flow or a nue ardente. This is known as basically a glowing avalanche. This appears almost like a snow avalanche, but this material is coming down the mountain at incredible temperatures and burning everything in its way. And this was what overran the city of Pompeii that we were talking about in some of the early slides. This is an example of a eruption of a pyroclastic flow in Japan. I actually won't play the video because the audio is not very good, but you can see it almost looks like a snow avalanche, but this material is very, very hot and it's moving at very rapid speeds, burning everything in its path. It was these pyroclastic flows that have done some of the most damage in terms of loss of life in volcanic eruptions. So this is St. Pierre in the Caribbean islands. This was a capital city of this region for a while. This was a time period in 1902 where much of the structures are essentially made out of wood. They may have some stone facades on the outer edges, but the majority of the structure is made out of wood. And there was a pyroclastic flow that occurred in 1902. This is the Caribbean islands, if you've ever been, are these beautiful volcanic islands that come out of the ocean. This is an island volcanic arc that we talked about when we talked about plate tectonics. This is two oceanic plates that are converging, and one of the oceanic plates is being subducted. And so instead of making a continental volcanic arc, like, for example, the Cascades, that includes the volcanoes of Mount St. Helens and Mount Rainier that we talked about, these pop out of the beautiful Caribbean Ocean. So great places to vacation. They make these beautiful landscapes, but they could be very deadly during eruptions. And so in this 1902 eruption, there was a pyroclastic flow. The estimates are that it was on the order of 450 degrees Celsius, and it was moving something like 300 kilometers per hour. Tragically, it wiped out the town with 28,000 fatalities. Here's a schematic of what that ash cloud and pyroclastic flow look like. So you can see the force in the center, the erupting jet, and the rising convective column that is pushing all that material up. But occasionally, as material gets off to the sides, it starts to get taken over by gravity, and it starts to fall and run down the flanks of the volcano. That's what we call this pyroclastic flow. When we talk about volcanoes, we essentially classify them into three types, and that depends on their shape and their size. And so we'll touch on these each individually. The first is a shield volcano. A shield volcano is named that because it looks like an ancient shield. It has this gentle slope, this kind of round concavity to it. This is an example for in the lower picture of the big island of Hawaii. So that's Mauna Loa, the active member of the Big Island volcanoes on the Big Island. And this is really predominantly created because the flows that are coming out are mafic, or what we would call basaltic. So they flow over long distances, they don't pile up on each other very much, so they create a relatively gentle slope, and they're relatively non-explosive. Cinder cones tend to be much steeper, and they are created mainly not of lava flows that are very coherent and held together very well. They're mainly made out of that pyroclastic debris that we talked about, so material that's sputtering out onto the surface. It almost looks like a pile of sand that you may create on the beach with a crater in the center. You can see that there's a flow leaving this one going north. This is, again, one of these cinder cones that's near the San Francisco Peaks in Arizona. There's a nice basaltic flow that's moving north there, or up in the picture. And you can see all the other material that's been sputtered around the sides that create this relatively small but relatively steep flanked cinder cone volcano. The most common type that we think of, I think, when most people think of volcanoes, are what we call stratovolcanoes, or sometimes also called composite volcanoes. This is kind of this classic volcano shape. So the little inset image there is Mount Fuji of Japan. The last eruption there is 1707, but that's also an active volcano that's relatively close to the urban center of Tokyo. These are very explosive volcanoes. They are dictated by primarily rhyolitic and andesitic lavas, so lavas that are intermediate to felsic in composition, so they are relatively high in viscosity. They have a high resistance to flow, meaning that when these things erupt, the lava doesn't flow very far. It starts to kind of build up along the flanks, and you end up creating this relatively steep but relatively small in terms of diameter volcano as compared to, for example, something like a shield volcano like the Hawaiian Islands. So you can see this, the flanks are much steeper, but the overall shape is relatively smaller, not nearly as small as a cinder cone, but much smaller than, for example, a shield volcano. And when things erupt, it's going to be dictated by what the chemistry of the magma is. So we've already mentioned this a few times. And this is the classic example of Hawaii, an eruption that's occurring along one of the flanks of the Mauna Loa volcano. This is a vent that's on the flank. We call this an effusive eruption. This is mainly basaltic lava. It's low in viscosity. It's associated with shield volcanoes. And it's relatively safe. It's never going to really have an explosive eruption. It's going to erupt in a much more gentle manner that we call effusive eruptions. That's very different than, for example, what happened with Mount St. Helens. So here are some of those images that we looked at in the very first introductory slide. And in the very first picture, you can start to see that there's a landslide that occurs. So in the image on the top right, there's these two major blocks that are sliding down the mountain. The mountain grew this large protrusion on the side of its flank as pressure was building inside the volcano. That pressure was building inside the volcano because the magma type below the surface had a very high viscosity. It had a high resistance to flow. And thus it was kind of clogging the conduit, the pipes that were allowing this material to move. And so it could build up a lot of pressure. And when that pressure was released because there was an earthquake and then a landslide that really slid a good chunk of the mountain down, you're talking about one of the largest landslides ever recorded in human history. half the mountain starts to slide in essentially two blocks. There's an upper block and then a lower block. That relieved all that pressure, right? You can imagine shaking up a 2-liter bottle and then opening the top. You relieve all that pressure and all that material comes spewing out onto the surface. And that's because this was primarily a rhyolitic lava. It had a high viscosity, and this is what creates an explosive eruption. Here are some images of Mount St. Helens prior to the 1980 eruption in the upper left. You can see it has that classic stratovolcano shape to it. Almost kind of looks like a pimple growing on the surface of the earth. And then you can see an image from the same angle. That's a lake there that's right next to the volcano after the eruption. And so a good chunk of the mountain was blown off. It was a lateral eruption, so the blast actually wasn't directly straight up. It kind of came out the side. You can see how there's a portion of the crater that's much lower than the back portions. You may see some steam rising there too, because this volcano isn't done with its life cycle. There's a new dome growing in the center. The thought is that at some point it's going to start looking like the top left image again as that dome fills in, and eventually it will have another large eruption. And so it's probably done this multiple times. Thankfully, this isn't surrounded by a large populous area, for example, like Mount Rainier is near Seattle. So there was only 57 casualties. Obviously, that's still tragic. And there was about $2.7 billion in damage. And volcanic activity is not random. This is an image of plate tectonics. So the red lines here are the different types of plate boundaries. You can see where we have mid-ocean ridges and things like that. And in blue, we have the Ring of Fire. So this is a thing that you may have heard about. This is a chain of volcanoes that essentially surrounds the Pacific Ocean. The Pacific Ocean is kind of unique in that the Pacific Ocean is now being consumed at almost every boundary that it exists on. It's really the Atlantic Ocean that is now dominating, and the Atlantic Ocean continues to grow, and the Pacific Ocean continues to shrink. And so that's the Ring of Fire, is the fact that there is so much subduction going on along the edges of the Pacific Ocean as the Pacific Ocean is subducting under things like the Philippines or Japan or the Aleutian Islands near Alaska or the Cascade Range or Central America. If you ever get a chance to go, there's beautiful volcanoes in Central America. My wife and I actually did our honeymoon in Costa Rica near Arnal, which is a beautiful volcano that you can go and experience and hike on, and there's some zip lines. But that's because there's an active subduction zone along the central coast of the western coast of Central America. And so the Ring of Fire is essentially this subduction zone of all of the edges of the Pacific coast, or the Pacific plate. And you can see that these volcanoes aren't random. They tend to be associated with areas that we have subduction zones. There's always going to be exceptions to the rule. Hawaii, for example, in the center of the Pacific Ocean. This is one of these hot spots that's an exception to the rule. But in general, the volcanoes that we have on the planet are dictated or are essentially there because there's a subducting plate. Each volcano kind of occurs in a general setting as a general rule of thumb. So for example, stratovolcanoes occur where we have ocean-ocean convergence or ocean-continent convergence. And so this is, for example, the Cascade Range that we talked about, or the Aleutian Islands. Shield volcanoes are usually associated with hotspots. So there's our example again in the center of the Pacific Plate of Hawaii. And when we talk about volcanoes, we really are thinking about them now in their life cycle. We're thinking about, are these active volcanoes, are these dormant volcanoes, or are these extinct volcanoes? And this becomes very important when you start thinking about policy making, about granting new building permits, and about insurance purposes. An active volcano is something that has erupted recently and is likely to erupt soon. Now, soon is a very subjective term. In geologic terms, we're probably talking about millennia. Dormant volcanoes means that they haven't erupted for hundreds or maybe thousands of years, but they still have the potential to erupt. And then extinct volcanoes are essentially volcanoes that have no chance of eruption anymore. The magma below the surface is all solidified, and all we see is the remnant of the volcano. Here's an example of an extinct volcano that you may have seen in some movies, for example. If you ever had a chance to go, this is a beautiful site. This is Devil's Tower in Wyoming. This is essentially what is believed to be the neck of an ancient volcano. That volcano existed millions of years ago, but has now subsequently gone extinct. So there's no new magma below the surface, and erosion takes over. And as the erosion continues to whittle away the mountain, what's now left is part of the most solid material in the middle that was essentially the neck of the volcano, where the magma was flowing to the surface and eventually becoming lava. So let's talk a little bit about predicting eruptions, because that's essentially what it all comes back to. We want to understand how volcanoes work and what the hazards associated with them are, because we eventually like to be able to make accurate predictions and mitigate the loss of life from future eruptions. There's a few ways that we can predict eruptions. We can look at a few different things that we'll touch on real quick individually. Things like earthquake activity, the changes in heat, the changes in shape, and increases in gas and steam emissions. So earthquake activity is one that we have known for a long time. So prior to the 1980 eruption of Mount St. Helens, there was a lot of warnings that Mount St. Helens may be getting close to an imminent eruption, because there was a lot of earthquakes occurring. And you can imagine that if magma is moving below the surface and it's breaking the rocks to make room for itself, very sensitive equipment at the surface will start to pick that up. These aren't going to be these very large earthquakes that we may be thinking about that are going to create tsunamis and things like that. These tend to be smaller earthquakes, but they're occurring very rapidly. We call them earthquake swarms. And with sensitive equipment, we can actually pick that up. And if we identify earthquake swarms in certain areas, we may be identifying the possibility that there's a eruption on the way. Occasionally, this can lead us astray, though. In the late 80s, there was an earthquake swarm around Long Valley Caldera. There was some orders for evacuations of areas like the Mammoth Mountain and the surrounding areas, and there was no eruption. And so it's a very fine line about how much warning you can give. And if you're going to evacuate people and then nothing happens, the next time that you provide a warning, it becomes much more difficult for people to actually listen to you, right? This is essentially the boy crying wolf scenario, where if you just continuously warn people that something's going to happen but nothing ever happens, then each time you warn, people don't really listen to you as much. There could be changes in heat flow. So if we think about an eruption that's getting closer to occurring, that means magma is getting closer to the surface. Again, you probably wouldn't be able to recognize this, but we have probes that we put a few meters into the ground, and they actually can be very sensitive to very small changes in heat flow. And so if we start to see that there's an increase in heat flow, that may be a telltale sign that there's magma moving closer to the surface. If it's closer to the surface, it's got an easier chance now to get through the surface and eventually erupt and become lava. And so changes in heat flow are telltale signs that an eruption may be imminent. Also, changes in shape. At Mount St. Helens, this was another kind of giveaway. There looked like a big blister that started to form on one of the flanks of Mount St. Helens. When this was accompanied by the changes in the earthquake swarm and also the increase in heat, it was really clear that there was magma moving close to the surface on one of the flanks of Mount St. Helens. It's thought that that eventually was what triggers the landslide. It weakened the flank of the volcano so much that when there was a small earthquake, it triggered that giant landslide that eventually released the pressure. But if you see that there's a change in shape, that is usually a telltale sign that magma is creating space for itself below the surface, and that means it's getting closer to the surface and possibly closer to an eruption. And then increases in gas and steam. So this is a zoomed in image of what we saw on that postcard from Mount St. Helens. This is the new lava dome that's growing inside Mount St. Helens. It's too dangerous for scientists to go there, but what they do is they lower scientific equipment on helicopters, and they put it along the flanks here, and so it's measuring heat and steam and gas emissions. And so we know that this lava dome is actively forming a new peak to Mount St. Helens, because we can see the steam coming off, and we know there's heat right below the surface, and we can measure the increases in gas emissions. And this is usually a telltale sign that an eruption is imminent. Just like with earthquakes, unfortunately, we're not very good at making accurate predictions. There's been a lot of advancements in technology. We've learned a great deal about the life cycle of volcanoes and how the volcanoes work, but we still have a very difficult time in accurately predicting a short-term prediction of saying the volcano is going to erupt tomorrow. We're pretty good at saying there's going to be another volcanic eruption in the next this many decades or this many centuries, because we can look at the recurring lava flows along the flanks and we can see that there's this recurrence interval, very similar to what we do with earthquakes. But it's very difficult for those to actually have a pattern where they go off every 110 years or so. It tends to be that these things range, from a couple, maybe every few decades to every few centuries to every few millennia. But in geologic time, that's a good recurrence interval. And we suspect that if the plate is continuously being subducted, that these volcanoes will continue to have these recurrence intervals. But there's a big difference, especially on a human timescale, between a few decades and a few thousands of years. And so we're pretty good at understanding the recurrence interval in a long-term fashion, but we still have a very hard time in making accurate short-term predictions. And the truth is that there's millions of people at risk because there's millions of people that live near active volcanic centers. Here's just an image of Mount Rainier again with the Space Needle in front. And so you can see Mount Rainier has its nice peak. Something on the order of 4 million people live in the vicinity. And again, it's not a matter of if Mount Rainier will erupt explosively. It's a matter of when and how much warning will we have. Obviously, we're not moving the city. We're not going to move the Space Needle. But if we can have enough sufficient warning to get millions of people out of danger, that would be a huge win for Earth science and understanding how the Earth works. Interestingly, there's volcanoes on other planets as well, not just on Earth. So if you look at the moon, the face that you see on the moon is usually the dark features, right, surrounded by some white areas. Those dark features are what we call lunar maria. Those are areas of basaltic flows, and they're kind of round in a lot of areas, and it almost looks, some people think it looks like a face, and that's because the low viscosity basaltic lava that's coming out, it's filling in the bottom of craters, and craters tend to be circular features. These are impact craters on the moon, and that lava fills these craters in, and so you get these nice dark circles in certain areas. And so the moon had active volcanism all the way to about 3.6-ish or so billion years ago. It is cooled subsequently, and we don't think there's any active volcanism on the moon today, but clearly it was active at some point. The largest volcano in the solar system is on Mars. We call that Olympic Mons. It's a Martian shield volcano. It's debated whether it's extinct or still active, but it is much larger than any mountain on Earth, and that's because the mass of Mars is about 1/10 that of Earth. And so that means that the gravity is significantly lower. So mountains can get bigger on Mars because the mechanical strength of rock we don't think is going to really change whether that rock is on Mars or that rock is on Earth. This is likely basaltic flows that created this volcano. But if you have a much lower gravity, you can create a much bigger pile of rock before you lose that mechanical strength. And so a volcano on Mars can get much, much bigger than a volcano on Earth. In fact, here's some images of Olympus Mons. The cliff face there alone is something on the order of 7 to 10 kilometers. So this is a huge shield volcano. It's still debated whether or not it can have some active volcanism. Here it is in comparison to, for example, Mount St. Helens or the Hawaiian Islands. So in the lower image there, that's, sorry, not Mount St. Helens, Mount Everest. So in the lower images there on the left, that's Mount Everest. And people think that Mount Everest is the biggest mountain on Earth, but actually the Hawaiian Islands are actually, the big island of Hawaii is bigger. So that's the big island of Hawaii. Unfortunately, only a little part of it is sticking above sea level. So in overall elevation, it's not taller than Mount St. Helens. Mount St. Helens is I keep saying Mount St. Helens. Mount Everest is the tallest mountain on the planet. That's in the Himalaya, right? That's due to continent-continent collision. And it's on the order of 28 or 29,000 feet. But the big island of Hawaii with Mauna Kea and Mauna Loa, if you measured it from the bottom of the ocean floor, would actually be taller. It would be on the order of a little bit over 30,000 feet. And so, but from sea level, it's only about 14,000 feet tall. If you compare that, and so what's in the background there, that's Olympus Mons. So Olympus Mons, the flanks alone are almost as tall as Mount Everest or the Big Island of Hawaii is. Just the cliff on the edges. And the overall elevation of the mountain is on the order of 3 to 4 times as high as, for example, Mount Everest is. And so it's a huge mountain, by far the largest volcano in the solar system, due to the low gravity on Mars. There's moons of Jupiter that are active volcanically today. So this is an image from the Galileo mission that was touring the Jupiter system and looking at some of the Galilean moons. And so those are the 4 moons that Galileo identified. One of them is Io. Io's very close in orbit to Jupiter, and it's so close in orbit to Jupiter that it actually gets pulled on by Jupiter's gravity, and Jupiter's gravity distorts its shape a little bit. And when it distorts its shape, it creates a lot of heat. And so what you notice is that during one of the flybys of the Galileo mission, they were taking images of the surface of Io, and they were noticing all of these dark areas that looked like volcanic activity. But then during a subsequent pass over the same region, they noticed a new dark area. And this was clearly a new eruption that had occurred in the time period between the last pass and the pass that they were doing now. And so it was clear that Io is actively volcanic right now. And in fact, it's likely the most volcanic planetary body in the solar system because of the effects of the gravity of Jupiter. Well, all right, that's all we have for our lecture on volcanic eruptions. Again, thank you so much for listening. Please subscribe to this channel if you can. Please follow me at Matthew Wielicki on Twitter, and subscribe to my Substack, irrationalfear.substack.com. And I will see you back here for the next lecture, which we will discuss mountain building. Thanks again, and have a great day.